In this video, I'll talk through the 2023 Advanced Higher Chemistry paper and explain how I would approach each question, starting with the multiple choice question number 1. We're asked here about the ground state arrangement of electrons. Two things to consider. First, we fill 4s before E, and also look for special stability. A, we're filling degenerate orbitals before we've got single electron in each of those orbitals, so that one's wrong. For B, we need to go to 4s before the 3d, so that one's not going to work. Again, C, we've not filled the 4s one first. That means D has to be correct. We'd fill the 4s and then we'd have 5 singly arranged electrons in the 3d. Next up, we're asked about shapes that need non-bonding electron pairs. They are sometimes referred to as lone pairs. If you have no lone pairs, you are able to have a linear shape. That is not going to be our answer. We could also get trigonal planar, tetrahedral, we could have trigonal bipyramidal, and lastly, if we had 6 pairs, we could have octahedral. The answer to our question is going to be trigonal pyramidal. Trigonal pyramidal occurs when you have 4 pairs of electrons, 3 of them are bonding pairs, 1 lone pair which distorts the shape, and that will give us the answer of C. Next up, we're asked about which block in the periodic table this element is. It's on the right hand side. If you've memorised your blocks, this will be nice and easy. You have your S block, you have your P block, you have your D block, and you have your F block. Our element is going to be one of the P block elements. Another way you can do it is if you roughly know which element you're talking about, you could write out the arrangement for that chemical. If we said it was something like phosphorus, it would need to be 1s, 2, 2s, 2, 2p6. That gets you up to 10. Then got 3s2, and you're going to have your 3p. We would have 3 left over. Your outer electrons are in a p shell, therefore it's a p block element. B would be our correct answer. Moving on, we're talking about heterogeneous and homogeneous catalysts. Hetero means that they're going to be in a different state. Homogeneous means they're going to be in the same state. This means we can rule out, well, B cannot be correct because that doesn't match up correctly. C can't be right because that doesn't match up correctly. Now we're talking about the absorption onto the active sites. For there to be adsorption onto the active sites, you would have your catalyst. You'd need to have the areas where they're able to bind to. This would be easiest to occur if they're in different states. So if you had gaseous reactants floating around, being able to join on to the active site, that would make A our correct answer. In dealing with titration curves, we need to look at where our equivalence point would be. That is the halfway point in the vertical section of the graph. That is a line to come across. Roughly speaking, around about 6 or 7 on the pH scale. If you had a weak acid and strong alkali, this would give you a pH change at above 7, so that is not going to be the answer. If you had strong alkali added to weak acid, well, again, you're going to get above 7, so that's not right. Strong acid is added to a weak alkali, you would get a slightly below 7 pH, and the same with the other one. Next up, we need to decide, well, what's happening to the pH? Well, we are starting off at below 7. We are starting off with our acid, and the acid is being neutralized, which means the pH is increasing. So we have got a weak alkali being added to a strong acid because we're starting at below 7, and then it's going up toward 7 and past 7 as you add more and more alkali. Next up, we're talking about an acidic buffer. Species absorbing excess H plus ions. That's going to need to be your conjugate base. If the conjugate base picks up the hydronium ions, that will turn back into your weak acid. Get rid of these 2. And a species that provides H3O+, that's going to be acting as your acid base. That would then give me an answer of D. Here, I'm talking about a feasible reaction, one thing we need to know is that if delta G naught, if we have delta G naught is negative, then it's going to be a feasible reaction. So standard free energy is delta G, gives free energy. So let's get rid of C and D. If it's going to be feasible, this means it's going to happen. Going from the reactants to the products, it's going to be favourable. Equilibrium, we need to favour our products. That would give you an answer of A. In question 8, we're asked to calculate the delta G naught for this reaction. If we go to our data booklet, we're going to deal with delta G naught equals the sum of the delta G naughts for the products, take away that of the reactants. Dealing with the products one is going to be your dinitrogen tetroxide. This means that we're going to need to use 97.7 kilojoules per mole. We want 1 mole of that, so we only want to use that equation once, which gives us that number there. We're going to be taking away. If we look at our second equation, we are using nitrogen dioxide. If you look at how you would turn nitrogen dioxide into dinitrogen tetroxide, we're going to need to times that by 2 in order to get to the 2 nitrogens we need to make the dinitrogen tetroxide. We can use Hess's law, we can combine the equations, which I will do in a second, but that would lead me to believe we're going to use 51.8 and we're going to times that by 2. The negative here is taking into account that we're reversing this reaction, and this should give us an answer of minus 5.9 kilojoules per mole. Answer B. Show you how they combine. Let me do it at the top. We're going to have 2 nitrogen dioxide goes into N2 plus 2 O2. You would then have N2 plus 2 O2s goes to N2O4. Nitrogens will cancel out, the oxygens will cancel out. We've got our conversion that's happening, and we get our answer of B for that question. Moving on, we're talking about an endothermic reaction. This takes in energy from surroundings. And positive entropy change. We are increasing disorder from a solid to liquid or liquid to gas. Let's have a look here. Burning gives out energy. It's exothermic. Get rid of that one. If snowflakes are forming, the flakes are forming from water. They're going to be cooling down. That means they're going to be giving out heat to the environment, so that's not going to be our answer. If something's evaporating, it's taking in energy to warm up, and it's turning from a liquid into a gas, or from a solid to a liquid then onto a gas. That one's looking good so far. Here we've got gases forming solids. That's going to be decreasing the disorder, so lowering entropy. That one's ruled out. C is the only one that makes sense. We're looking here for the rate determining step. The rate determining step will involve the chemicals represented in the rate equation, so X and Y. B does not have X and Y, so it's ruled out. It could be C, because you've got your X and your Y. However, it's making the end product. It's not an intermediate step. I'm going to rule that one out. Here we have XY, which isn't in the rate equation, so we're going to rule out that one, leaving us with our answer of A. This means that your next step could be taking your intermediate, reacting it with the second Y involved, and making Z. So your second step might be intermediate plus Y goes to Z. And when you put those together, you end up with your overall equation. Here we're asked about single bonds. We are talking about a sigma bond. Our sigma bonds are our end-on overlap. If it was a pi bond, it would be side-on. I'm going to rule out the 2 side-on ones. In terms of the shape of it, it depends on the 2 chemicals that are joining together. We have the same chemical joining together. You would have a symmetrical orbital. because the pools from both of them are equal. If one of them had a higher electronegativity, you might end up with an asymmetric orbital. So A would be your correct answer for 11. Over here, we're talking about a chromophore that absorbs blue light. They absorb blue light, they would be promoted, or the highest occupied orbital, the lowest unoccupied orbital, so HOMO to LUMO. That would give you then A or C. Next up, if it absorbs blue light, we see complementary colour. That means we won't see blue-green. We need to see a different colour. To prove it's red, you could look at the colour wheel, and the colour wheel is hopefully going to have red across from blue-green, which we do. That gives us our correct answer, hopefully, of C for question 12. Next up, we're looking for things that do not exhibit hydrogen bonding between its molecules. We are looking for hydrogen directly bonded to F, O, or N. We have an alcohol group. We have OH, which means it does have hydrogen bonding, is not our answer. If it's an amine, it's got an NH2 group. We have N directly bonded to hydrogen, which has hydrogen bonding, does not have, it's not our answer. We have ethanoic acid, which will have a carboxyl group. Again, has an O direct bonded to H. Won't be our answer, leaving D. Ethoxyethane is an ether, so you've got an oxygen sandwiched in between your carbons. It looks something like that with all your H's. That gives us D as our answer. We're converting a haloalkane into a ketone. So we've got that turning into something like that. Okay, so typical way of getting a ketone is from alcohol, the oxidation of an alcohol. So we need to try and take our X, which would be our halogen, so chlorine, bromine, whatever it might be. We would then, I believe, turn that into, got an alcohol group. It would need to be a secondary alcohol, like that. And then that could then be oxidized into your ketone. The first one's looking good because the sodium hydroxide would provide the hydroxyl group, and that could then be oxidized into your ketone. I'm going to end up starting with that one. And this one here, you would end up putting on a C triple bond N, and when you hydrolyze that, that would give you a carboxylic acid. That's one of the conversions you need to be aware of. I'm going to get rid of that one. Next up, we've got ethanol. So if you're using ethanol as your solvent, that's likely to be an elimination. That would give you a carbon-carbon double bond. That could, if you added on water, could end up with your hydroxyl group for your alcohol. I can't see how that would give you your ketone. I'm going to rule out that one for that reason. And then in the last one, we are doing a substitution. Got our ethanol. That's just not thinking to me. The substitution part, usually that would swap out one bit for another, which doesn't look likely here. Oxidation's the bit that's making me lean towards that. So I'm dealing with the fact that we know ketones are formed from oxidation of secondary alcohols. First part of A looks like it would give you an alcohol, so A would be my correct answer. Next up, we have got our reducing agent. And this takes ketones and aldehydes back to the appropriate alcohol. Here we have a C double bond OH. That means we have an aldehyde. And this will go to a primary alcohol, meaning there's one carbon attached to the carbon with the OH. The organic product, so we are talking about the alcohol, so I'm going to get rid of that one. That makes no sense to me either. That makes no sense. We're just getting it from that being an alcohol. If it was asking you if you had a few more primary alcohols, if you draw it out and look at what you've got, something like this, when you convert this, you're going to change your carbonyl group into an alcohol group. An extra hydrogen on it. 1, 2, 3, 4 carbons means it's bute. Butane 1-ol because it's on the first carbon. Methyl group off the second. 2-methyl butane 1-ol. I got that because it's the only alcohol that's present, but if there was multiples of them, you could use that way of naming them. We are looking at what reaction we are going to get from here. We'll get C4H8. We're adding on NH3. At the end, we're taking away H2O. So we're still going to have 4 carbons. Well, we would have 11. Take away 2 would be 9 of those. We would have 1 oxygen and we'd have 1 nitrogen. Now, does that help me? If I'm right, well, that doesn't look right. There's no 2 oxygens in that one. That would mean that, well, that has no oxygens in it. That has no oxygens in it. Then B would be our correct answer. Yeah, that's one way of doing it. Maybe a more scientific approach might be this is a condensation reaction. So we can make an amide if you've got a carboxylic acid, got our ammonia there. We've got our nitrile at the top, which isn't that. We've got our amide link there, C double bond O to N, so that would make sense. Whereas we've just got what would look like you'd make from a substitution if you substituted in the NH3, which isn't what's happening. And the last one looks kind of funky. Don't know how you get to there. But yeah, the counting up one kind of worked from there. Let's look at isomers now. They have to have the same molecular formula, but different structural formula. Methoxy means it's got CO. We'd have 3 carbons. And we'd put in all our H's. We've got C4, H10, and O. If we count them up just to make sure if there's any ones we can rule out, they've all got 4 carbons. That's not going to be the answer. Look at the H's. We've got 5, 6, 7, 8. So I'm going to rule out A. Next one has 10, so it could be that. Next one has 8, 9, 10 as well. And the last one has 6, 7, 8, 9, 10. So only A I've ruled out first of all. Else if you read the question saying which one is not an isomer. So A is the only one that doesn't fit the same molecular formula, different structural formula. This is probably because if you look in here, I think that would need to be C double bond O to allow it to have the correct number of bonds within it. So that's not going to be equivalent to the ether. So B, C, and D. Read the question properly. Make sure you're answering the question they're asking you. That'll make life a little bit easier. If we want geometric isomerism, we need to have restriction of rotation. Typically, that would be a carbon-to-carbon double bond, triple bond, or some sort of ring structure. Doesn't look like any ring structures there, so I would probably just go for a little sketching them out. We have got C with 2 H's, going to a C with 1 H, and the PR. This would need to have a double bond, so it would tick the box of having restriction of rotation. Next one, again, we've got a double bond, so that works out there. We have a double bond in here. Okay, bit cluttered here, but first thing is that they all have the restriction of rotation. The next thing we're looking for are the groups that are on each of the carbons involved in the double bond. There has to be differences between them so that you can end up with what's called the cis and the trans, so the arrangement of those attached atoms or groups of atoms. In the first one, we've only got one group that's different. Only the BR is different. So that's not going to let you make different isomers of them. So I'm ruling out A for that reason. Let's get rid of that. Next one in B. Well, what we've got is we've got a chloro group on the first and a methyl group off the second carbon. This would allow you to either have them both on the same side of the carbon-to-carbon double bond or on different sides of the carbon-to-carbon double bond. That's, to me, putting B looking quite nice. I'm going to leave it there just now. Next one, if we look at C, well, off of the carbon-to-carbon double bond, you have 2 chlorines off of the second carbon, and then you've got an ethyl group coming off of the first carbon. The 2 groups are the same, the chlorines, and that's why I'm going to rule out that one answer. When it comes down to D, we've got methyl, methyl, methyl. So there's 3 methyls with just 1 hydrogen. There's no different ways of arranging those, which is going to rule out that as our answer, because you can only really get one version of it. That would put B as our answer. And this would allow you to get 2 different versions, which, because of the lack of rotation around the double bond, you cannot spin them around to look the same. That's going to be your 2 different isomers of each other. If we're looking for something that destroys the compound, we are, in mass spectroscopy, you are breaking off fragments, you are bombarding it, splitting it apart. That's going to destroy the test compound. In infrared spectroscopy, you are making the bonds bend and stretch. That doesn't necessarily mean it's going to destroy it. If you melt something, you can just cool it down, then it will re-solidify. Depends if your product is likely to decompose at high temperatures, so it might. It doesn't always do it. In proton NMR, you're looking at the hydrogen environments. Again, it's not going to be destructive compared to A, which would be our correct answer. In a question like this, up until the last couple of years, it was usually just antagonist and agonist, talking about blocking and talking about mimicking things. An antagonist is the one that blocks the natural response. This rules out A in this one. However, it blocks the receptor sites, not the enzyme's active site. We're going to get rid of that one, just so we know that the agonist is our mimicking one, not that one. An inhibitor, an enzyme inhibitor stops the enzyme from working, so that's going to rule out C, and it does that by blocking the active site, and that gives D as our answer. For any biology, but for any biologists, this would be talking about competitive inhibitors versus non-competitive inhibitors, and this one would be blocking the active site, so it would be a competitive inhibitor. Next up, we are looking for the largest fragment, which is common to all 3 molecules. So we are looking to see what parts do they all have in common. So our first option would be this fragment here. However, we don't have that in the middle one, in dot sepin, so that can't be right then. Let's get rid of that one. Okay, if we look at the second option, well, we do have that in A. We do have that in B. And we do have that in C. So that is common to all 3 of them. But is it the biggest one? Let's check. Next up, got here. That does work for the first one. Not going to work for the second one because there's no chlorine. So let's get rid of that one. So C is not going to be right. D. Looking at D. And put that on top. So it matches the first one. Looks like it. Doesn't match the second one. Now, I think they're trying to trick us here, because if you look over here, that matches the first and the last one. But if you look at where it is, it's pointing the opposite direction. As in, you've got, so what I mean is you've got your nitrogen is going down to the right there. So, but here we've got it going down to the left. Now that won't make a difference because that would be a hydrogen there. All they've done in this one is they've kind of rotated around that bottom part, which is allowed to do it. Now that is bigger than the one for part B. So the way they've drawn it, it looks like it's trying to trick is, throw us off, my answer I would go for would be D, because it's just the orientation of it that matches. So it doesn't match exactly the picture, but in chemistry we can rotate around the molecules, and that's why my answer is going to be D for number 21. On to number 22. In this one, we have got our percentages of the two chemicals. What we want to do is we want to divide those numbers by the relative GFMs, and then look at the ratio between the two values that we get from that. Vanadium has a GFM. Okay, vanadium's GFM is 50.9. Put that in there. And then we want to use the oxygen one. We just want to use the single atom value, so just over 16. Pop those into your calculator. If we divide both of them by the smallest number, we get a 1:2 ratio. We have a 1:1 ratio in the first one. We have a 1:2 ratio in the second. The ratio is the wrong way around. And the last one, it's a 2:3 ratio, so not right. 22 will be answer B. Looking for a primary standard. These are the chemicals which are going to be available in high purity, stable in air and in solution. They have got a relatively high GFM. So which ones can we get rid of? Well, we have got quite reactive acid and base, so let's get rid of those ones. We've got calcium carbonate and we've got sodium carbonate. Calcium carbonate, or chalk, is prone to decomposition. If you heat that up, it will break down and give off carbon dioxide. It's not stable for that one, whereas your sodium carbonate is one of your primary standards. Other primary standards include oxalic acid. That's a good one if you are standardizing something like sodium hydroxide for a project or whatever. Oxalic acid is used quite often for something like that. Next one, we are dealing with ppm, parts per million. They've got two definitions depending if you're talking about volumes or you're talking about masses. So in this one, it's going to be 1 milligram per kilogram. Other one would be 1 milligram per litre, which we don't need for this question. So they're saying it's 420. That's going to be 420 milligrams per kilogram. And we have got 5.1 times 10 to the power of 18 kilograms. And 18 kg. So all we have to do, got that many times more kilograms, so we're going to have that many times more milligrams. That gives you 2.142 times 10 to 21 milligrams. If we are wanting to get that into grams, it's 1,000 times of a difference. So that would be 2.142 times 10 to the 18 grams. Then kilograms we divide by 1,000 again. That will be times 10 to the power of 15, which matches E. So 24 would be the answer B. Just your conversions between them of that. One thing that I think is quite handy to remember. So 1 kilogram is 1,000 grams. 1 gram is 1,000 milligrams. We were going this way. You would divide by 1,000 to turn it into grams. Divide by another 1,000, turn it into kilograms. People like to use 10 to the power of -3, whatever. That would be my answer. Okay, next up, we are asked to use our equations to do ratios to try and convert between different chemicals. So we are asked about iodine. And iodine is hiding here. Iodine, not iodide. Iodide would be the I minus. And we are told about Pb2 ions we've got from there. We're looking for chemicals that are in common between each equation. So what I mean by that is if we're starting off with the Pb2, and that is one of them. Now I want to jump to the second equation, so this one here. And I can see that they've got that in common. So the ratio of Pb2 plus to PbCrO4 a 1-to-1 ratio. So if we've got one of them, we would need one of them. Next, we're trying to jump between the second and the third equation. There's a mismatch between the CrO4 in the middle one and the CrO4 in the bottom one. So what I'd have to do is this bottom equation would have to be halved because we're only using one of the Pb2 plus. So what this would mean then is that if that now becomes a 1 because I've halved it, all the other numbers would half as well. And the most important one would be for the I2, because the ratio now, if we've halved everything down, well, between the PbCr4 and the CrO4 to negative is 1 to 1. Then we then add in our I2, that's now going to be a 1.5 in there. So it's a 1 to 1 to 1 to 1.5 ratio, which means our answer would have to be B. So we're trying to look at how they can connect between the equations, and you need to take into account we are fixed to say that it's one of the Pb2 plus. That's what the question says. So everything has to be based off using one of those. So if there's one of those, we would make one of those. And if you've got one of those, you would make 1.5 of those ones. So we need to take into account the ratios and get to our answer there. On to section 2 now. First question is asking about emission spectra and how we get different colours of light. When your electrons fall to lower energy levels, they will emit energy equivalent to red light. So some of the wavelengths is equivalent, whatever kind of thing we've got, but that's how you get your red light being emitted. Next here, we've got an electron in lithium positive ground state. So first of all, we need to look up lithium. Lithium is number 3 in the periodic table. That means it's going to have 3 electrons. Show you that. And we're over on the left. So lithium has 3. This means its arrangement would be 1s2 and 2s1. However, we have lost an electron. We're talking about a 1s electron. So the value of n is the principal quantum number. That is that first number that's here. So for our one, once it's lost its outer electron, it's going to be 1. If it was the other one, it'd be number 2. If L equals 0, that means it's an s orbital. Again, that's matching what we have said in here. So we've got our box, we've got our orbital. Next up, we're talking about whether it's pointing up or pointing down. So the magnetic spin, and that's going to be with a subscript S. So that's your magnetic spin quantum number, saying which way it's rotating within the orbital, and that gives us our answers there. Next up, we're asked to determine the oxidation state of the chlorine. We've got 4 options on them. So how I would do this is, we've got oxygen. Oxygen would typically be 2 negative, but we've got 4 of them. That gives you 8 negative. Overall, we've got a 1 negative charge. So 7 positives must be required to cancel down the 8 negative from the oxygens to leave you with 1 negative overall. So our chlorine has to be oxidation state of 7 or plus 7 to get us our answer there. If you're asked about sigma bonds, it's the first bond that's made. First bond made. Let's do a count. So we have got 1, 2, 3, 4, 5, 6, 7, 8, and 9. Answer of 9 sigma bonds. Think of it that way, it will make it nice and easy. If you're wanting pi ones, that's any second or third bonds after that. So in this one, there would be 2 pi bonds, 1 for each of the double bonds that are involved in this molecule, and that gives you an answer of 9. Next up, we're asked to calculate delta H. Again, we're going to use the products, take away the reactants. So our product is Fe2O3, but we've got 2 of them. So it's going to be 2 times minus 824. There is nothing for the reactants, so I don't have to involve them at all. I can just put that's going to be minus 1648. kilojoules per mole. Next up, we're doing it for delta S. We again are looking at our product, so we are dealing again with 2 times 87.4. However, we now need to take away, we've got 4 ions. It's going to be 4 times 27.3 plus 3 oxygen, so 3 times 205. I'm going to let my calculator do all the heavy lifting. That gives me an answer of minus 549.4 joules per Kelvin per mole. Looking for a temperature in Kelvin where the reaction is feasible. We are looking at when delta G is negative. And the way we do that is we use delta G equals to 0 in our calculation. So the first thing is we're going to be using delta G equals delta H minus T delta S. Delta G would equal 0. We need to make sure we're using the same units in both of them. So we can see that our enthalpy is in kilojoules per mole, but our entropy is in joules per Kelvin per mole. So we need to get them both into the same. For me, it's easier to change the enthalpy into joules per mole. So just times that by 1,000. You can do it the other way around. It doesn't really matter at all. We move T delta S across. T delta S will then equal delta H. So T will equal delta H over delta S. Putting in the numbers, I'm doing it this way around, so I would do minus 1648 with 3 zeros, by 1,000, divided by minus 549.4. Did it the other way around, you'll get exactly the same answer, so it doesn't matter. So that then gives an answer of 2,999.6 Kelvin. Probably just put that as 3,000. That would give you your answer there. So that is the temperature at which, below which it will become feasible, because when you go below that number, that will make your delta G not be negative, and that means it's a feasible reaction. Next up, got lots of numbers floating around. We need to try and come up with the minimum mass of sodium chlorate required to supply oxygen to 5 people for 8 hours. Right, let's do, I'm going to do with the average person first of all. So they take 0.38 litres per minute. So if we've got 5 people, that then needs to be times by 5. Let's do that first. That'll give me 1.9 litres per minute. And then 1 minute is 60 minutes. So we've got 8 hours. Gives you 480 minutes. So I'm going to need to times that by 480. That's going to mean they're going to need 912 litres for the 8 hours. So I've dealt with all of that. So next thing is that they're saying that 1 mole gives 36 litres of oxygen. If we need 912, when I'm dealing with scaling, I always go through the number 1. Makes life easier for me. So if I start at 36, if I divide by 36, that'll take me down to 1. And then if I times by 912, that'll take me up to the answer I'm trying to get to. And we do the same on the other side. I'm going to take my 1 mole, I'm going to divide it by 36. I'm going to times it by 912. And that means I get 25.3 moles of sodium chlorate. Not quite finished, because they're then asking us for mass. Mass equals number of moles times GFM. I'm going to need to use that 25.3, times it by GFM of sodium chlorate. Sodium is 23. Chlorine would be 35.5. Then your 3 oxygens, it's 316, so that would be 48. That'd give you 106.5. Pop that down here. And depends how you round it, but we should get 2,690, let's call it 94 grams. And that gets us our final answer. Rounding, we'll tweak it a little bit. If you use the unrounded number of moles, that would give you a different answer, but we're in that sort of ballpark region, and that would be your required mass. Question number 2 asks us about the kinetics of this particular reaction. When you're determining the order, you need to find 2 experiments in which the only difference is the concentration of the chemical you're investigating. Here, mercury chloride concentration, if we look at experiments 3 and experiment 2, as you go from experiment 3 to experiment 2, you double the concentration and you also double the rate. Therefore, that will be first order with respect to the mercury chloride. When it comes to looking at the oxalate ions, we want to be looking at experiments 1 and 2. As you double the concentration of oxalate, the rate is going to quadruple. That's going to give you a second order reaction. If you're not sure if it's quadrupling or doubling, if you just divide the bigger one by the smaller one, here we get it comes out as a value of 4. That means it's quadrupled. If it's quadrupled, that means we have a second order reaction. Next, we're asked to do the rate equation. We need to take into account the fact it's first order with respect to the first chemical and second order with respect to the second. K is the rate constant. We just need one of the concentrations of the mercury chloride. The oxalate needs to be squared because it's second order. That's how they come about. Next question, we're asked to calculate the value of the rate constant for this reaction. We take our rate equation from above. We're going to rearrange it to figure out what K would equal. So K would be rate divided by the concentrations, remembering to square the oxalate one. We can pick any of the experiments in the table. I'm going to go for experiment 1 just because it's the first one that's there. Popping those numbers in, we can then plug it into our calculator and we will end up getting our value of 2.56 times 10 to the minus 4. One thing we can do is we can just memorise that if it's a third order reaction overall, this is the units, or we can work them out using the units of the values from the table. Our rate is in moles per litre per second. All the concentrations are in moles per litre. We've got 3 of them because we've got our first one and then we squared the second one. MOL, L to the minus 1, MOL, L to the minus 1. We have MOL, L to the minus 1 on the top and the bottom. We can cancel them out. If we collect like terms, well, S to the minus 1 stays there. You've got 2 moles at the bottom, so that would be MOL squared. And then you've got 2 L to the minus 1s. That would give you L to the minus 2. You add them together. We want to get them all to the top line. The MOL squared on the bottom when it goes to the top will become MOL to the minus 2. L to the minus 2 when it comes up will become L squared. We've still got S to the minus 1. More typically, the positive powers will be written first. I usually go for the moles second, and then the S to the minus 1 at the end. They will accept any order that you want to put, but that's the one that I would probably go for in that one. Next up, we're asked to calculate the initial oxalate concentration for experiment 4. What we're going to have to do, we're going to have to do some rearranging and then some inserting of the values. So if we rearrange this means the concentration of oxalate will equal the square root of the rate, 2.11 times 10 to the minus 6. Divided by our 2.56 times 10 to the minus 4 times the mercury chloride concentration of 0.032. Plug that into your calculator. That gives an answer of 0.508 moles per litre. Moving on to question number 3. This question we are talking about precipitation gravimetric determination, it looks like here. First thing, what should be done to ensure the precipitation reaction has gone to completion? If you add more of the chemical that you're reacting to cause the precipitation, in this case calcium chloride, that will see if there's anything left over to react. Next, they're asked about what you should do before weighing to obtain an accurate mass. You want to heat it, dry it to a constant mass. That's where you heat it up, cool it down in a desiccator to prevent reabsorption of water. Do that until you get constant mass and you're ready to go on with your reaction. Next, we want the percentage by mass of oxalic acid given that we make 0.075 grams of precipitate? Well, the precipitate is going to be your calcium oxalate, which is the solid on the right hand side of the equation. We also need to know the GFMs of both of them, and that will help us in our calculations. So first, start with the calcium oxalate. We know the mass. We can work out the GFM. There's a GFM of 128.1. Work out number of moles. Gives you 5.85 times 10 to the minus 4 moles. You look at your relationship, you have a 1-to-1 ratio. So if you've got that many moles of the oxalate, you'll have that many moles of oxalic acid. GFM of oxalic acid, and it up at the top there, that gives you 90. Work out the mass of oxalic acid that corresponds to, 0.05265. Percentage by mass, we take that mass, divide it by the mass of the spinach leaves, 8.975 times 100, and you get 0.59%. Very small value, but there is only a little bit of precipitate that we are making. Why might you end up with a different value than what we calculated? Multiple different reasons. One could just be that there was a loss of product when you're transferring. Happens quite often. You might not have gone completely to the end of the reaction. If you'd had more time, left it for longer, that might have done something different. Or you might not have extracted all of the chemical that we started with. Any of those ones would pick up the mark. Next question is the first of our using our knowledge of chemistry questions. We're asked about concentrations of different ions in tap water and how you can determine them. One way we could do it is we could do some flame testing. We could look at the emission spectra that we get from that. Your things like sodium and your copper, they would give off different colours of light. And if you had more of that light given off, that would indicate there's a higher concentration. You look at what wavelength of light would correspond to different metals. That would be one thing we could do. Second thing we could do is we could look at complexometric titrations using something like EDTA, ethylene diamine tetraacetic acid. If you had the correct indicator like muroxide, you could carry out a titration. If you had a higher concentration of the metal, you'd require more of the EDTA to bind with it. That might work for things like aluminium and the magnesium that's involved. We could look at a redox titration, something like the iron could react with potassium permanganate. Again, if you've got more metal ions, you'd require more permanganate. You could add in redox equations. At this point, I'm not going to do that, but that is an option for you. You could use your absorption spectra. You could look at the absorbance of particular wavelengths of light. And again, that would indicate if you've got high absorbance, it'd be a high concentration. Calibration curves and stuff like that could be used as well. You could do gravimetric determination of the sulfate. If you convert that into barium sulfate, that will precipitate out. You could measure the mass of the precipitate, and if you had higher concentrations of sulfate, you'd make more of the precipitate. For questions like this, you need to give a limited answer for 1 mark, a reasonable answer for 2 marks, and a good answer for 3 marks. It doesn't have to be complete, excellent, or very good. Just want to try and pick up as many marks as you can, and something like this should hopefully pick us up our 3 marks. Next question, we're talking about transition metal complexes. We're first asked to write the electron configuration of the nickel in this reaction. First thing I would do is check the number of electrons that nickel atoms have. Nickel has 28 electrons. Next, I would write out the full configuration based off of 28. Where you have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. Next, we work out how many electrons have been lost to make it an ion. In aqua, the OH2 is water, has a neutral ligand so it doesn't get involved. This means that the Ni must be 2+. When you have a transition metal, you're going to lose the 4s electrons before you lose the 3d. That would make our arrangement for the nickel ion 1s2, 2s2, 2p6, 3s2, 3p6, 3d8. If you first worked out those 26 electrons, you would probably end up with your last two parts being 4s2, 3d6, you have to be aware, you have to remember, you fill the 4s first and you also lose from the 4s first. Doing it this way means it shouldn't be a problem. Put it out as if it was complete, had all its electrons, and then take away the 4s and any other electrons you need to do that. Next one, we're looking at the name of this complex. We've got an amine ligand. That's spelled A-M-M-I-N-E. There are 6 of them, so it's hexaamine. Next up, you've got to look at, is it a positive or negative complex? This is positive, therefore we just write nickel. We don't need to worry about nickelate or anything like that. It's a positive complex overall. It just gets written as is. Similar to before, the amine is a neutral ligand, therefore we don't need to worry about the charges on that. The Ni has to be 2+, and that's why we have the Roman numerals 2 after it, and that gives us our answer there. Next up, we're asked to classify this type of ligand. There are 3 of these ligands that have joined on. Each of the ligands is making 2 bonds. We describe that as being bidentate. It's making 2 bonds to the metal in the centre. If it was 1, it would be monodentate. You get hexadentate, it would be 6, and you get polydentate, describing anything that has multiple bonds. Coordination number is just how many bonds is the nickel in the middle making. It's making 6 bonds. That's the answer for the coordination number. Continuing with the transition metals, we're first asked to explain why the solution of this chemical would be green. All to do with D to D transitions and splitting. The electrons will be promoted to higher D orbitals, and that's done by absorbing purple light. We would then see the complementary colour of green. If you're not sure of your colours, colour wheel will help you significantly, and we're looking for the colours that are opposite each other. So green and purple are complementary. So if you absorb purple, you will see green. That's what we have there. Next up, we're asked to talk about the greater ability to split ligands. If it has a greater ability to split, it will have a bigger energy gap, which means it will absorb smaller wavelengths of light. Looking at the graph, the one with the O2, the one with the OH2, that absorbs higher wavelength light. So we're looking for the one with the ammonia, the NH3, because that is absorbing light at a lower wavelength, which would correspond to higher energy. So something like the NH3 causes lower wavelength light to be absorbed, higher energy gap from a greater ability to split the ligands. And that would go together. If the question was the other way around, well, the other one, the aqua one, absorbs light of longer wavelength, therefore it's a lower energy gap. In this question, we're asked about equilibrium constant. Equilibrium constant, we're looking at the products divided by the reactants. In this case, there's 2 HIs, which means when we're doing the concentration of that, we have to square it at the top, and then we've got the other 2 concentrations multiplied together on the bottom. Next one, we want to work out what the value of K would be for this reaction. We've got a few pieces of information. The question says that we've got 0.25 of the 2 reactants. We would have none of our product. At equilibrium, we've got 0.015 moles of the iodine. This means we must have used the difference between them, 0.235. It's a 1-to-1 ratio. We must have used the same number of moles of the hydrogen. It's a 1-to-2 ratio between the reactants and the product. Therefore, we must have made 0.47. So that's how much we'd have at equilibrium. All we need to do now is stick those values into our equation that we've worked out. Popping them in, typing them into your calculator, we end up with a value of 981.8. No units for the equilibrium constant. That is our answer there. Next up, we're asked to calculate the energy of light. We're going to use E equals LHC over lambda. You can get those values from the data booklet down on page 20. That will give you 6.02 times 10 to the 23, 6.63 times 10 to the minus 34, 3 times 10 to the power of 8, all over. We are given it in nanometers. We want to use meters. Just pop on times 10 to the minus 9 onto your wavelength. Stick it all in your calculator, and this will give you 207 kilojoules per mole. When you type those values into your calculator, it will come out in joules per mole. So it'll be 207,000. Divided by 1,000, turn it into kilojoules. Just be aware of what numbers you've got. Some of these people convert it beforehand, it doesn't really matter. And the next question, we're asked about the type of funnel that we should use to carry out vacuum filtration. We're looking for a Buchner funnel. Buchner funnels look something like this. It allows you to apply a vacuum to help quickly filter it. Next, we're asked about the percentage yield. Couple of things we need from the top. First thing we need is that we've got our mass of iodine we're starting with. We've also got our ratio of 1 to 2 between the two chemicals. First thing I would do is turn the mass of iodine into the number of moles, doing the mass divided by the GFM. It's I2, so we want to times our GFM by 2. That will give us 1.123 moles. It is a 1 to 2 ratio, therefore we'll have 2.246 moles of the hydrogen iodide. Next up, we would turn that into a mass by timesing by the GFM. That'll be 126.9 plus the 1 for the hydrogen. That gives you an answer of 287.3. That theoretical yield is bigger than the actual yield, which is good. Actual divided by theoretical, plop in the numbers, and calculator says 87.4% as your answer for that one. In this question, we're asked to follow a mechanism they've given us to apply this to a different chemical. If you look at the top, they have split the starting material into 2, and they've changed the OH into a double bond O. Difference with the next one, it says it only gives one product. We don't need to worry about the breaking apart, but we still want to convert those hydroxyl groups into carbonyl groups. So I can take this and I just have to replace the OHs with double bond O's, and that gives me my final answer. These ones are designed to look complicated, but if you can pick the bits that change, you just change those and leave everything else the same. Sticking with some equilibrium here, we're asked to explain the effect of increasing temperatures on the concentration of carbon dioxide. First thing to check is that we have a negative enthalpy change, therefore it's exothermic, which is favoured by a cooling, a lowering in the temperature. Therefore, an increase in temperature will favour the reverse endothermic reaction. That means that the carbon dioxide will be in the gas form, which means that you will decrease the concentration of dissolved carbon dioxide. So favours reverse, lowers the carbon dioxide concentration. Next, we're asked to compare the strength of carbonic acid with ethanoic acid. pKa of ethanoic acid is 4.76 from the data booklet. The higher the pKa, the weaker the acid. The lower the Ka, the weaker the acid. So in this one, carbonic acid has the higher pKa, which is equivalent to the lower Ka. Therefore, it will be the weaker acid than the ethanoic acid. I tend to work with Ks rather than pKas, but just the opposite way around. So higher pKa means that you've got your weaker acid from that. We're asked about the role of H2O. If you look at what's happening, H2O has gained a hydrogen. That means it's acting as a proton acceptor, which is a base. The carbonic acid is given up, it's donating a H+. Unsurprisingly, that makes it acting as an acid. And this question, we're asked to calculate the concentration of hydronium ions given the pH, which is based off of pH equals minus log to the base 10 of the hydronium ion concentration. If we rearrange this, this will give you that the concentration will equal 10 to the power of minus pH. That will be 10 to the power of minus 8.2. Calculator says that is 6.3 times 10 to the minus 9 moles per litre. Next one, we're asked for a percentage increase between two pHs. Well, we already know the concentration of the first one. If we apply this same calculation to the 7.9, we get 1.259 times 10 to the minus 8. If you want a percentage increase, take the two of them away from each other. That gives you 6.29 times 10 to the minus 9. Divide by the original, which is the 8.2's value of 6.3 times 10 to the minus 9. And that gives you, rounded a little bit, to 100%, 99 point something percent. That is your answer for that one. Next one asks about a back titration. How do we do that? First, you want to react your chemicals with a known volume and concentration of, in this case, hydrochloric acid. That will be done. That allows you to work out the number of moles of acid that you've added. You then want to react the leftover excess hydrochloric acid with your sodium hydroxide, and that will determine how much was used up, and you can work backwards to how much calcium carbonate was present. When we're dealing with a control for something like seashells which contain calcium carbonate, just use pure calcium carbonate. You carry out your experiment, you should get a value of 100%, because that is how much calcium carbonate is in pure calcium carbonate, and it can be used to check how well your experiment's working, if it's getting the right sort of results you need. In this question, we are asked about crown ethers. If they look weird and confusing, that's because I think they slightly are. So here we've got something called 18 crown 6. It tells us that it's to do with the total number of atoms and also the number of oxygen atoms that are involved. There are 18 atoms in total. There are 6 oxygens, 18 crown 6. Looking at the one that we are given, we've this time not got 18, we've got 15 atoms, 15 points. There are 5 oxygens, so 15 crown 5 would be the answer we'd be looking for. Next, they're asked, what would you use to complex with lithium? They're getting smaller as they go. In the data booklet, we see that the chemicals that they are complexing with are getting smaller. We are going to want a smaller crown ether. We went from 18 down to 15. We went from 6 down to 5. That would mean that we could either use 12 crown 4 or 9 crown 3. Having a wee sketch of these, it might look something like this, where you've got your 12 points and you've got your 4 oxygens. Alternatively, you could do something like that. It's a little bit more messy in my one, it's a bit smaller and a bit tucked in, but those ones would work out, to pick up your answer for that one. Talking about ligands have to be able to donate lone pairs. So these chemicals are capable of donating lone pairs of electrons, making those dative or coordinate bonds. In this one, we've got 1, 2, 3, 4, 5, 6 carbons. So each of the points at which it changes direction would represent a carbon. So that's C6. We've got at each of the points where the carbons are, there are going to need to be 2 hydrogens to make the carbons make 4 bonds. So we've got 2 carbons from the OHs, and then 2 from each of the carbons. So that'll be 2, 4, 6, 8, 10, 12, 13, 14 H's. There's 4 oxygens as well, which gives you C6H14O4. If you're not too sure how to work with the skeletal formulas, you could draw it all out. Just maybe it takes a wee bit longer, but you'd be able to get the same answer as well. In this one, we've got our OH groups are reacting with the Cl's off of the second chemical, and they are joining together, and then we're forming our cyclic product. This looks to me like a condensation reaction. We have a small molecule being produced when 2 molecules join together. So I would aim for, or I'd write condensation as my answer for that one. Next up, we're asked to calculate a maximum concentration. What information are we told? First of all, we're told a number of milligrams, which I will convert into grams. We can then work out our number of moles by doing mass over GFM. Tells you there it's 264. Gives you your number of moles. Next, look at our ratio. It's a 1-to-1 ratio. Therefore, we're also going to have 0.00085 moles of the potassium. We are asked to work out in moles per litre. So we can use C equals N over V. That number of moles, the volume was 350 centimetres cubed, or 0.35 litres. And that gives you a concentration of 0.0024 moles per litre. This question's asking us about different representations. This one seems a bit contrived to me. I don't really think it's the best using your knowledge question I've ever seen. What kind of things are we going to talk about though? So if we talk about, first of all, the full structural formulas, they show you all the bonds in the molecule, which will tell you information about functional groups. So you can expect specific peaks at different spectra. You can look at the fragments for mass spec. So are you expecting a carbonyl group, etc. You could also see if there's potential for geometric isomers. If you've got double bonds or rings, that would stop the rotation and that would allow you to kind of know that about it. Molecular formula, you can't really see, or you can't distinguish between isomers, aldehydes and ketones of the same number of carbons, would have identical molecular formulas. Primary and secondary and tertiary alcohols as well, you wouldn't know which one you've got just from the molecular formula. It's harder to see reaction pathways. Do you have an ester or a carboxylic acid? You don't know that. You don't know what reactions it could do. The skeletal structure could identify chiral centers, maybe easier than a full structure. So for example, in this one here, that carbon on the right hand side, well, one in from the right, that has 4 different groups attached, therefore it'd be classed as being a chiral center. That's probably easier to see than in a full structure, perhaps. You could also get some information about the hydrogen environments for your proton NMR, and knowing about if something was cis or trans, that could give you information about melting points and boiling points. Again, we just need to be good to get the 3 marks. I would hope that's covering the points that the SQ would be expected. I'm not 100% sure. This is the least sure I've been about one of these for quite some time, but those are the things that sprung to mind, and that's what I would have ended up talking about. In this question, we're asked about conjugated systems. Conjugated systems have alternating carbon-to-carbon single and double bonds, which we can see in here. We're asked about the type of hybridization. We have got 3 types of hybridization we need to be aware of. sp3 you'd find in the alkanes, sp2 in the alkenes, and sp in the alkynes. Here we've got butadiene, that means it's going to be sp2 hybridization. We're then asked to follow the reaction that's above and make the product for this reaction at the bottom. Things that stick out to me, well, we've got our carbon-to-carbon double bond there, which is still present. These 2 double bonds will break, and that will join up to make the other half or the other part of the ring. We apply the same logic to this one. What we end up with, if I scroll down, we're going to keep the carbon-to-carbon double bond there. You've got a methyl group coming off of the remaining carbon-to-carbon double bond, and then we would have our CN sticking out of the other side, and something like that should pick up the mark. In this one, we're reacting cyclohexane. We're talking about molecules becoming polarized. You have got lots of electrons in the double bond of the cyclohexane. This will repel the electrons. This will cause there to become a polar bond instead of a non-polar bond in the chlorine, and that allows the reaction to happen. When you've got your intermediate, when you're breaking up a carbon-to-carbon double bond, so the electrophilic addition reaction, we're going to come up with a cyclic intermediate where one of the chlorine atoms is joined on in a little ring. That would have a positive charge. Next one, we're asked about geometric isomers. Again, it's the lack of rotation. This time, the lack of rotation around the ring. It's a cyclohexane. Next up, we're asked to draw an isomer, still being a cyclic isomer. It does not have an optical isomer. This means there is no chiral center. If we draw out our ring, if we put the same atom on each of the carbons, there is no carbon that has 4 different groups attached to it. Therefore, it does not have any chiral centers. Therefore, it will not be optically active, and there's no optical isomers. In this question, we are reacting our cyclohexene with HCl. First thing to remember is that that's going to give you a polar bond, which is going to make it more likely to react. We've got our cyclohexene looking like this. We've got our HCl. The double bond, the electrons in there, will be attacking the H. That's slightly positive. That will kick out the electrons in the bond, and that will break apart that bond that we've got there. That will leave you with your intermediate that's got your ring, a positively charged carbon, and then you've also got your H on there. That chlorine that was kicked out is now negatively charged and will be attracted to the positive carbon, the carbocation, positive. That will then join up to make your cyclohexane. Double bond's broken, and we get to there. Here they give us one of their funky formulas with lots of different new words for us to be confused by. We are asked to calculate dipole moment. That means we are using our equation that we've got that equals Q times R. The R is the bond length, needs to be in meters. That's why I've written 0.127 times 10 to the minus 9. So for Q, it tells us Q is the partial charge times E. So our partial charge is 0.178. E is 1.6 times 10 to the minus 19, says in the question, times by our bond length in meters. Make sure it's in meters. That then gives you the number of coulomb meters. However, the question wants it in D, which is your dBs. It tells us that 1 dBi is 3.34 times 10 to the minus 30 coulomb meters. So if we take our coulomb meters, divide it by the value for 1 dBi, and that will give us an answer of 1.08 dBis. Lots of places to go wrong if you don't convert into meters, if you don't spot that we work out coulomb meters and we want dBis, you're going to end up with an incorrect answer, but that is our final answer for that one. This question we need to see, well, what's changed from left to right? Well, we've added now an NO2, we've substituted that in. Electrophile means it's going to be attracted to a negative charge, that's going to be positive. So NO2 positive would work as the electrophile in this question. In this question, we're dealing with our curly arrows. We're trying to show what's happening as we are going through these different resonance states where electrons are moving. We've got our negative charge is moving into the ring, and that's breaking up a carbon to carbon double bond. So what would end up happening is we'd have our electrons being transferred into the ring. We would break the double bond that we had previously. When it asks you then to go on and say, well, what would that produce? Well, we would end up with our ring again. The negative has moved around, rotated round, and we've got our double bond towards the bottom. The top part of the OH has not changed at all. That's going to stay exactly as is. And that gives us our structure for structure 2. Next question, we're asked what type of reaction is taking place. We are taking an NO2 and turning it into an NH2. We're losing oxygen. We're increasing the hydrogen. That's going to be a reduction reaction taking place. In this one, we're asked to suggest a reagent that could be used to carry out this experiment. We have an amine turned into an amide. This can be done by reacting it with a carboxylic acid. And the particular carboxylic acid that would make sense here, we're adding 2 carbons, so ethanoic acid would make sense. When you're recrystallizing, you first want to dissolve in a small volume of hot solvent, cool it, and then filter it. And that will get you your purified sample, in this case of paracetamol. Important is hot solvent, small volumes, cooling, and then filtering. In this question, we're asked to identify the bond in paracetamol that gives rise to 1660. We have got these bonds to play with. Those are the only ones that are present. That's going to be the best. We've got our C double bond O splits. We've got our C double bond O stretches. That ticks off all those values there as well. The ones that are slightly above those as well. So my best answer for that one would just be the carbonyl group that's present there. We have to look at the functional groups again and see why is it going to be difficult to look at values above 3000. Heading up to there, we have got OHs, we've got NHs, stretches as well. That both of those are present in our chemical here. That means it's going to be likely that they would overlap, and it'd be hard to know exactly which of those has given rise to those peaks. So something along the lines of those would cause similar graphs, and then it might overlap and kind of obscure where they come about. Yeah, something to do with that they're very similar values that would end up with those. Next, we're asked about our high resolution NMR. Here we're asked about the 2.1 shift, which is a singlet. There are no hydrogens on adjacent carbons. That gives us 3 possible environments that would give rise to a singlet. The one that I've circled in orange, the methyl group, that would have a higher height because there's more hydrogens in that environment, whereas the other two would correspond nicely with the OH and the NH. Another approach you can use to determine that would be looking at the table in here. 2.2 fits in nicely with aldehydes, esters, amides, etc. Whereas the OH and the NH would work out nicely with the values that are a bit larger. The shift as well just fits nicely with some sort of CH3 group present in there. Next, we're asked about the multiplets that would be seen for the other peaks. We're talking about the other hydrogens that are involved. They have got one hydrogen on adjacent carbons. That would give rise, using N+1 rule, to a doublet, or in both cases would be doublets because they're in similar environments. Last question, they're asking us about purity from a low resolution NMR. The table tells us we're expecting 5 peaks. In our graph, we have got 6 peaks. However, that final peak would be our reference peak. Tells us on page 17 that the 0 ppm is for the tetramethylsilane, the TMS reference. That means we can ignore that. So there are 5 peaks present, which would indicate it's a pure sample that we've got. The peaks correspond with the expected environments, so that all is looking good. If you were to confirm, or if you were to look for the purity of your sample, you can use a few different techniques. The one I would use would be a mixed melting point. So take some of the pure sample, mix it with your sample, measure the melting point. If you have a narrow range which matches with your expected literature ranges, that means you've got a pure sample. If you've got an impure sample, it would have a wider range, and then the values would be different as well. They'd be lower. So you're looking for that range to match nicely, and that would indicate you've got quite a pure sample. You could also use chromatography, so thin layer chromatography. If you have a pure sample, you would see only one spot on your chromatogram. So if you'd made only the product you wanted, you would have spot at the same point as the pure sample. Your RF retention factors would be the same. If you had an impure sample, you'd end up with extra spots at different places, which could be unreacted chemicals, or it might be a byproduct, side product that in purity, just sort of depends. Either of those ones would pick up your mark, and that would give you your final couple of marks. That's how I'd approached each of those questions. Thanks for watching. Goodbye.